logistic regression, the basic idea of it is that it's regression when you have a binary outcome. What have we said that regression is? So a regression is just a model for the conditional expectation of an outcome given predictors, right? So given that you see predictors take a certain value, what do you expect that the outcome is? And you assume that follows some function f. In linear regression, we assumed that f was of the form a plus bx, where x could be multiple predictors and b could be multiple coefficients. So we made that assumption, and then we found the best a and b that we could. If y is binary, so an example of a binary outcome, it could be, let's say you're trying to predict who takes a certain treatment. Some people don't. It's anything that's 0, 1. Some people get diagnosed with a disease, some people don't. So if you have an outcome variable that's of that form, the expected value of that outcome, assuming you code it as 0 if you don't, 1 if you do, is the probability that the outcome is equal to 1, given the covariates. So a way to make that intuitive is that expectations are means, right? They're averages. And the mean or average of a whole bunch of binary variables or realizations of a binary variable is just the proportion of ones. If you take the sum over a bunch of ones and zeros and then divide by the total number, that's the formula for the mean. And that's also just the proportion of ones. So conditional expectations of binary variables are just conditional probabilities that those variables are 1. So given that a plus bx is not a great choice for a model for a probability, because probabilities are between 0 and 1, and a plus bx is not necessarily, especially as x gets large, it'll eventually cross the 1 barrier or the 0 barrier. If you extend a line, it's not gonna stay between 0 and 1 forever. So it will eventually give nonsensical predictions, and it's automatically not properly specified as a model. Although it could be well enough specified, like within the range of data that you see, and it's not crazy to use a linear model, even for a binary outcome for that reason. But yeah, it's not the best choice. So what we want is a regression model where we say the probability that the outcome is equal to 1, given that we observe some values for the predictors, is equal to some function of the predictors, where that function is bounded by 0 and 1. So there's this function called the logistic function, or the inverse logistic function, that has that property. So x here, don't take that to be the predictor variable. Just think of that as like the input to this function. The inverse logistic function takes its input, call it x. It takes e to the x and divides it by 1 plus e to the x. So you can see that it will never be greater than 1 because the denominator is always 1 higher than the numerator. So this can never be greater than 1. It will approach 1 as x gets very big, because like 8/9, 9/10, 11/12, right? That's something over 1 plus something, 12/13. As that gets really big, it approaches 1. 7/8, 8/9, 9/10, 10/11. You're getting closer and closer to 1 with these. So you can see that here, that the function of x, logit inverse of x, approaches 1 as x gets very big, but it will never get bigger than 1. And similarly, as x gets very negative, e to the x approaches 0. So this thing approaches 0 over 1 plus 0. So it approaches 0. This logit inverse function just makes things S-shaped. And so that they approach 1 and they approach 0. And in the middle, it's kind of semi-linear. Remember, we were looking for a function that would be bounded by 0 and 1, and that we could use to make a regression for y given it. And we were saying just using a plus bx for a regression wasn't good, because as x got really big, it would go past 1 on one end and go past 0 on the other end. But if you wrap a plus bx inside this inverse logit thing, you make sure that it's bounded by 1 and by 0. And you can still have the probability depend on x in kind of a natural linear way inside the inverse logit function. Let's say the bigger x is, the more likely y is to be 1. Well, then what's inside the inverse logit function will get bigger when x gets bigger. And the probability that y equals 1 will get bigger, but it'll never exceed 1. So that's the whole idea of logistic regression in a nutshell. It's a way to still model the relationship between y and x, in particular, the conditional expectation of y given x, if y is binary. And so that your expected values for y are always between 0 and 1, as they should be. Here's an example where you have a equal to negative 1.4 and b equal to 0.33. So the bigger x gets, the higher the probability that y equals 1. So here's an example from regression and other stories. These two plots are the same. They just zoomed in on the part of the x-axis that actually contains observations on the right-hand side. That's a zoomed in picture of what's on the left-hand side. One of the main authors of this book is a political scientist, so that's why so many of the examples are political. So it's the probability of voting for George Bush Sr. as a function of income quantile. 1 is poor, 5 is rich, and it's modeled as an integer, even though you could view it as a categorical variable. For the purposes of this model, it's like an integer. It's just increasing income on the x-axis. And you can see when you plot logistic regression data, the outcomes are all going to be 1 or 0. But you can see by looking at this that in the poor x value, it's a lot more kind of densely populated, right, at the 0 level than at the 1 level. So it's more common to not vote for Bush Sr. if you're poor. It's harder to see anything visually for 5. For 2, still more likely to not vote for Bush Sr., right? These dots are both denser blob than these dots. For 3 and 4, they're both kind of 50-50, and indeed that's like what the predicted value is from the logistic regression. And yeah, 5, it's hard to see visually, but according to the model, at least, you're more likely to vote for Bush Sr. at 5. Right? Because you're at like 0.6 probability if you're at the income level 5. On the right-hand side, they also show what you could essentially view as bootstrap estimates of this regression curve. Like the little gray lines are if you had resampled the data and then refit the regression, what would the curve look like? So it gives you a sense of what's the uncertainty of this surrounding this curve. As we learn about logistic regression, we're going to use it to do basically the same fundamental tasks that we were doing with linear regression, and those are description, prediction, and estimating causal effects. There are going to be differences, though, which we're going to highlight along the way. So interpretation of the coefficients is different. That's a big example. We would often interpret a linear regression coefficient as all other things held equal. If you shift this coefficient by 1, at least in the non-causal case, covariate by 1, you expect the outcome to shift by the coefficient on average, right? If people who have value of the covariate 1 different from each other will on average differ by the coefficient of that covariate. That's what we say in linear regression. But for logistic regression, if you shift x by one, the amount that y shifts is very different depending on the value of x, right? Like up here, when you're close to 1, the probability of y barely changes when x goes up because you're already so close to 1, there's nowhere to go. The slope is actually maximal in the center. The interpretation of the coefficients is different and a little more unwieldy with logistic regression. Diagnostics and model assessment are also different. There are still notions of how well does this model fit, like where we had residuals with linear regression. You could imagine residuals are a little trickier here when it's just 0 or 1, right? The residual is going to be either this difference or this difference. It's not like a smooth cloud, right, of residuals. And this R squared notion is going to be different. How well do you predict a binary outcome? They're going to be different. And I think actually maybe easier to interpret notions of assessing how well the model fits and how well it performs. Code-wise, it's pretty similar. You just this function GLM instead of LM, essentially, where the G stands for generalized. So it's a generalized linear model, not just a linear model. Generalized meaning in the special case of a linear model, this conditional expectation is just equal to a plus bx, but generalized linear models are like a whole class of models where you can wrap the a plus bx in different functions. And for logistic regression, you wrap it in the inverse logit. For regular linear regression, you wrap it in the identity function, just like multiplying it by 1, or just not wrapping it in anything. It's a special case. And then there are also other options. So the code is quite similar. You still specify what's the outcome, what are the predictors, using outcome squiggly predictors, using that formula notation. R is doing something different under the hood. It's fitting the model, finding what the best A and B are, what the best coefficients are, using a different procedure, which we'll go into a little bit because it will help for understanding the behavior of models. You can still use logistic regression for standardization if you want to estimate an effect on a binary outcome, just like you could with linear regression. You can also estimate causal effects by modeling probability of treatment given confounders using logistic regression, and then adjusting for confounding using something called propensity score weighting, like an alternative way to estimate effects of like binary treatments other than standardization, which you can do by fitting a logistic regression model for the probability of treatment given confounders. This is just like a roadmap for all the stuff we'll talk about with logistic regression.